the renormalization group in terms of momentum's language. And we're starting with the Landau-Ginzburg-Wilson theory, which is just a 5-4 field theory. So before I get back into it, let's just reiterate the logic behind this. So we're separating out slow and fast modes, is what I'm calling them. Okay. So slow and fast is just a name. I'm not even sure that we didn't make it up. And what it means is we're doing an integral in the Brouillon zone, which has a UV cutoff. But then we are dividing the momentum space into a shell of fast modes that we're integrating over, we're tracing over, and then an inner sphere of slow modes that we're keeping as degrees of freedom. So that's the analogy of, again, the spins within a block, within, and then the block spins, which are our new degrees of freedom after this RG step. Okay, and that's everything inside here. So we've written our fields in K space as just a sum over slow and fast. Okay, so that frames the problem in terms of momentum instead of real space. Then we're going to integrate at some point over the fast modes. That's equivalent to doing the trace over spins within a block in real space. Remember we did a trace? And we wrote everything in terms of, I don't know what, sigma primes in the Ising model. And then we have to rescale. So then we take our new degrees of freedom, which are contained within, say, that inner sphere, and we rewrite the problem by rescaling everything so that our action looks self-similar to this action, but it only contains the degrees of freedom within there. So we have to rescale momenta because we're in momentum space. So K prime. And we have to rescale the slow modes, which involves knowing the relationship between the fields before and after the RG step. So I'm just calling that wave, for now it's just Z. This should be B to some scaling dimension, right? We'll derive that today. And so if you think about it, what you're going to do is you're going to get an action, S prime, after one step of the RG, that has rescaled fields and rescaled momenta. And the parameters, say R and U in this case, are what we're going to write the RG transformation as. So that's going to be the equation that we study in terms of calculating critical exponents. It's the relationship between R and R prime and U prime. So our goal is an action or a functional that looks like phi prime phi prime squared, that's not a 12, plus u prime over 4 phi prime. So it's very analogous to what we did in real space. We're just trying to find the same form. And then we can represent each functional with this just pair of, the only thing different is sort of the r's and the u's. It's the same as saying our Hamiltonian has parameters, k. Maybe it's a temperature in a field, right? And the RG is basically encapsulated in how those k's transform. So t to t prime or h to h prime. So in this case, it's r and u. That gives us critical exponents. Tells us where our fixed points are. Fixed points are when r star are when r star and u star just don't change under RG. Right, so now our RG flows are going to be written in terms of R and U. And the correlation lengths scale accordingly and so on. Okay, so that's what we're working towards. This is the RG framework in essentially momentum space using that phi-4 theory. And so what I was getting at last class is that we can split that action into two pieces. One's Gaussian, which involves the first two terms, here and here. And then the phi-4 term is what screws you up. It makes it so you can't do the Gaussian integral. And we need approximation techniques for that. Okay, and this is something that, we try to sort of Landau, Ginzburg, Wilson with fluctuations. And higher order terms in this expansion screwed us up. So we've reframed the problem in a very different way. We're now looking at some sort of RG picture, but we're still going to have to do some approximation at some level for this term here. Okay, so last time I don't remember how this worked. I'd written, okay. I'd written S in terms of slow and fast fields. And I argued that the Gaussian part splits into two pieces, which will make integrating over the fast modes in step 2 hopefully easy. What I contend is the interacting piece that comes from phi-4 is going to be a little bit more complicated. You have slow and fast fields, and you also have that delta function, which relates all the k's. So in this case, the delta function just gave you the field squared. It was kind of simple. In this case, that delta function relates everything. You get all this mixing. We're going to start looking at this eventually, but let's just not make any assumptions about the interacting piece of the action now and just carry it through. So that'll set us up for a bit of a cleaner expression at the end. Okay, so So once I have this written down, I can just write the partition function as a functional integral. Right? So I have to have a functional integral over all the fields. But I'll just write it as a functional integral over fast and slow separately. And now that we have this set up like this, let's attempt to do the integration over the fast modes. Okay, so it's the outer shell that we're trying to thin out the degrees of freedom. Okay, so after the integration, we're just going to write the partition function, which again is invariant. But now we've somehow integrated out all the fast modes. And what I want this thing to look like is a partition function member of the same form. You basically want it to be self-similar, so you force it to look like this, where now it only depends on slow fields, so the inner orange shell up there, but my S prime is something different. So I hope my S prime looks like this, or I have to force my S prime to look like this. And I have to actually convince myself that I don't generate higher order terms, phi 6, phi 8, because that was the problem that's the problem I told you happens in real space RG and higher dimensions, is you generate all possible terms in the Hamiltonian consistent with the symmetries. Right? So right now we're just going to assume that the form stays the same, and we're going to have to justify this at some point. And actually the reason it's justified is we'll find that higher order couplings, so if I have a phi 6 and a phi 8 and everything, that those couplings are irrelevant. Okay, so that's not obvious at this stage. But I'm talking about relevant couplings, remember, like temperature and field. These are going to be relevant, higher order ones are going to be irrelevant. That's going to justify in the end the fact that we have sort of a self-similar action. Okay, so let's just keep that in mind. So we've integrated the fast modes. Now, what does that mean? We can pull out this piece that only depends on slow modes out in front of that integral. But the other two parts have fast modes as arguments. So I need the integral over fast modes. That's my D. So one of them's Gaussian, and one of them's interacting. Okay, so I can do a trick to write this as an expectation value, basically evaluated with respect to that Gaussian piece. So I'm gonna multiply and divide by this part of the functional integral. So it's just unity. Yeah, let me pull this up in here. Just for now. Okay, so I want to divide this by. It's like I can't remember how I make these D's. There. Ah. I'm just multiplying and dividing by that. Sorry to jam it in there. So this, and this. So what this does is it lets me write, okay, this is like a partition function, right? So it's like one over the partition function, integral, right? The same kernel as the partition function, and I just have this piece, so it's like the expectation value of e to the minus s int, right? Evaluated in that Gaussian, with respect to that Gaussian action. Okay, so let me call this, I don't know, Z. It's Gaussian, Z naught, but it's also fast. So this piece, I'll write as the expectation value. It's Gaussian and fast, and Z, Gaussian and fast. So that expectation value is essentially the central problem that you need to solve. And you'll use Wick's theorem and Feynman diagrams and all sorts of stuff to solve that. Okay? But for now, what this tells us is the form of our action, the thing that we're, S prime, the thing that we want, has some least constraint. That's not here for the slow fields. And then let me just take the log of this. And also minus log of that partition function. That thing's just a constant. It's like the analogy to G. Remember G? It's a thing that was stuck in the free energy or whatever after all the like integration or all the tracing out of the spins within a block. Compared to G of K, I think I called it. Okay, so that's a thing which you'll drop because it doesn't contribute to like thermodynamic estimators. So that gives you that's not slow. So your action's almost the same, except you got this big mess. Get my S interacting. Okay, so that's, now let's assume that this form, you know, is the same as, is self-similar to the original And I say we'll justify that later in more detail. But also I want to write in momentum space. That was real space, right? And we did that last time. We did the Fourier transform. So just very generally, I want to relate this to S prime in momentum space. So most importantly, that it only has terms up to phi 4. That's what's important. And then write in momentum space what we expect this self-similar form to be. So I'm going to do the Fourier transform. So I'm going to have R's and U's occurring, but I have K squareds and all that stuff, remember? So if you look back at your notes, what I'm aiming for is this. So I have an integral over just the slow modes, right? Everything left. Now I had K squared plus what? K squared plus R. K squared plus R, right? So let me just assume that those two terms have coefficients that we have to determine, right? We have to constrain this by this in order to determine what K squared plus R looks like. So let me just introduce two new variables. I'll call them tilde. I'm going to call them prime in a minute, but I want to relate primes to unprimes carefully. So I've just assumed a general form for K squared plus R, and I got to figure out what these two coefficients are. Then remember I had a slow field, right, like this, right? So that's my Gaussian piece, you know, constrained to be self-similar after one step of the RG. But I also have a phi 4 piece, which is a big mess. And there's only one coefficient, which is U, so I'll just call it U tilde for now. Remember, you had 4 Fourier transforms. You have 4 fields. And we want to integrate out fast fields, so we're constraining this to look like this. And we need that delta function. So it's 2 pi to the d delta function k1 plus k2. So again, remember in the Gaussian case, the delta function just relates two momenta. K1 plus K2 is 0. So that gives us 1K, and we make it K and minus K. That's why this looks like this. This is the just, you know, 4 variable extension of that same delta function. I've just left it in here. But that's the thing that causes all the constraints between all these fields. So I've written it, I'm enforcing this form so that it's self-similar. So it's all over slow modes, right? I'm going to rescale the slow fields to be the new field phi. And so what I need to figure out is the relationship between these things and U tildes to the original R's and U's. And that gives me this. This is what I'm chasing down. Does that make sense? Okay, so there's just a few general things that we can say. So I've kept this very general. We want this to be some r prime plus k squared, okay? But so now what we're going to do is rescale. Okay, so I have fields and I have momenta. So that's like step 3 here. So I know how to rescale my field, but I don't know how to, sorry, I know how to rescale my momenta, but I don't know how to rescale my field in Fourier space. So that's what I need. And furthermore, whatever that scaling dimension is for the field has to make, you know, this look like r plus k squared. So the coefficient of k squared should be 1, okay, multiplied by a half. You know, yeah, we basically need that's called the wave function renormalization. Okay, let me do this rescale step, and then I'll calculate z. So it'll look like okay, so my new rescaled fields are just the slow modes rescaled, right? The upper limit is now my new UV cutoff, right? So it's like rescaling, you know, the block spins to be your new degrees of freedom. You have momenta, dd integrals, but they're k primes now. Each one of those picks up a b, right? You invert this to the d, and there's 4 of them. No, sorry, there's not 4 in this case. I jumped to the interacting one. I was looking down here. So there's only 1. So for the Gaussian term, it's b to the d. R, R2, you can call those anything. There's a k squared, so now I have a k prime squared at the expense of a b. I've rescaled my field here. So I need a z squared. Now my slow-mo becomes my field, k prime squared. Make sense? Did I do it right? Yeah, so this piece has 4 integrals. So u tilde, rescaled, 2 pi d, these are primed, 4 b, right, so minus d, and there's 4 of them. I got 4 fields that I'm rescaling. Phi prime k 4 prime. And then 2 pi to the d and the delta function. Does that delta function pick up a rescale factor? It's got it, right? B to the D. I was going to write that there, and if it's wrong, it'll screw us up later. I think it's right. Okay, so we need Z. How do we get Z? What's the strategy? We know the scaling dimension of the field, right? Because when we did the scaling dimension of the 2-point function, we derived the scaling dimension of the field just from the scaling ansatz. So, you know, that was in real space. Is it the same momentum space? You don't know. You gotta try it, right? You gotta Fourier transform it, and then whatever that Z turns out to be, this thing and Z have to conspire with this so that the K term is, you know, the coefficient of the K term is unity. If not, then we're not self-similar. So let's derive Z. I think I did this, yeah. Okay, so you got to remember back when we did this, that I'd originally written this in terms of probably sigma, but it's the same scaling dimension. Now we're talking about some fields. So I just want to Fourier transform the field. So it's just basically the definition of phi k. And then x is what? B times x prime, right? What else do I need? Oh yeah, so then this is what I'm doing here. dx is b dx prime, and d to the dx is b to the d dx prime. So this thing, e dx, rescaled at the cost of b to the d, phi prime, x prime. And the field is rescaled at the cost of its scaling dimension. And I forgot the exponential in there. E to the k and x, the scaling dimensions cancel, right? So I should just have e to the minus I k prime dot x prime. Okay, so now I can just write this as, you know, phi prime with some factors. Something happens here. Oh, I got b to the d and b to the minus d. But that is just phi prime k. So that's the scaling dimension out front here. Phi prime, yeah, k prime. And you know what that is. We argued the form of YH in last class and how it relates to the anomalous dimension and everything. d plus 2 minus eta over 2. Okay, so that means our z, how's that? Our z is that. B to that scaling dimension. Let's do minus eta over 2. Okay, so if you plug that in up in that Gaussian piece, so just look at the factors of b. You have b to the minus d, b to the plus d, b to the minus d, b to the plus 2. And then you have just eta left over. So it means that R2 has to be, b to the eta. So that constrains that. And remember that anomalous dimension is most of the time 0. Like in Landau theory, which you know now is the Gaussian piece of this, you know that that eta is equal to 0. In the mean field theory. Okay, makes sense? So that gives us, that's just the Fourier transformed version, but let me call, R. So now R naught tilde is R prime, and U tilde is U prime. And that gives us this equation here. Yes? Okay, so it's R naught b to the minus d. You have to take all the scaling dimensions, and that gives you. So let's just do the Gaussian piece. Let's do the explicit RG transformation just for the Gaussian piece. Okay. And then we'll shake that relationship out. Questions on this? The scaling dimension. This makes sense?
But maybe like how do you know there will be no contribution from this segment integral to the value of we scale R and U? So,
you don't. There will be. There will be. Yeah. Yeah. There. So this is general right now, and if I what I'll do is I'm going to throw away this last piece and say that U is 0. But the difficult part is when this comes in here and then R and U get mixed together in the RG transformation. Yeah. So that's a good question. You don't know. So this is the general form here with this kind of identification of R2. Again, just something to keep in mind for when we do this in general. But yeah, so that's the difficult problem. So let's forget that second piece, that second integral, and just do the Gaussian case. Okay. All right, so then the rescaled form of that function, k prime b to the minus d, r naught, it's r2, we constrain that thing. Okay, so that's what we're gonna consider, and I already said the coefficient. Must be a half. That's 1/2 b minus d plus 2 minus d minus 2 minus eta z squared. So that's a constraint. And let's just set the anomalous dimension eta equals 0. We know a priori that that's the case for the Gaussian theory. So then, putting all this together, only one field, 2 pi d. I got b squared r naught tilde plus k prime squared phi prime k prime squared. Okay, so if we compare back to our original momentum space action for the Gaussian theory, right? So the only thing that looks different is here. And that's what we called R originally, right? So that thing is our R prime. So I'll call it maybe R naught, I don't know. I'm mixing notation. And in the Landau theory, that R, or R naught, whatever I want to call it, is, so, you know, it's just the reduced temperature, right? It's just T. Or at least it's proportional to T. That's the thing that changes sign. Remember, to make your parabola go upside down? So this gives T prime is B squared T. So that's basically the only RG equation in the Gaussian case. Which is fine, because you know there's only one relevant variable, and that's that temperature. So the scaling dimension, which we called y subscript t, is 2. Right? It's just that power. And we are, you know, from our scaling hypothesis of the last, whatever, few classes, that say your critical exponents, like nu, are related to these scaling dimensions. So now we know that in the Gaussian theory, nu is 1/2. Is your mind blown? How many times have we calculated that? You know, we just keep doing the same thing over and over again in all these different ways. So remember before it was the, you know, we had the 2-point correlation function. This the correlation length was defined as e to the minus r over the correlation length, and that was a square root. As a square root as a function of t minus tc, and that gave us the same exponent. So here we've basically done exactly the same thing in momentum space. You already know that the Gaussian part of the Landau-Ginzburg-Wilson action corresponds to mean field theory. So here you get the mean field critical exponent just like you should, but now you've done it by looking at the RG equation, which comes out of just enforcing self-similarity and looking at how the coefficients scale. So this tilde, now that I look back, this tilde is a little confusing. I was keeping things general, but that R naught tilde is your R, and that other coefficient R2 tilde I could have just called some constant or some function of B. So we know what it is in principle. So that defines the the mean field exponents. And if I had a field in here, a magnetic field, like a term linear in phi, that's what I need to get y of h. But I just didn't do it, right? So if you want all the other critical exponents are the ones that need y of h, that scaling dimension, you got to put the field in the action. That's all you got to do. It's as simple as that. So just looking ahead, it won't always be this simple. When we start putting in this phi-4 term, you're going to get all this mixing between t and u's. So let's just make a few notes about kind of notation. So the RG recursion relationship, that thing. R prime equals B squared R. That's the thing you're analyzing, right? In this case, it's so trivial, it doesn't matter. But it's really this equation, the analysis of that step, which gives you all the power of the renormalization group. So that relationship is usually written different. So that it's by defining B as, it's sometimes written as e to the delta L or just e to the L. That's just defining some L. Or delta L. So delta L is somehow it's like you want to form a derivative in the RG step. So R prime R to the E to L in our case, and I would expand that exponential. So just linearizing everything, making that delta L small. So that lets you define a derivative. So that derivative looks like, I'll call it R prime minus R. It's like how your variables depend on that RG step. So in this case, it looks like that. L parameterizes the RG step. So that equation's the same as writing 2r. And the fixed point's required, or the fixed point is found by requiring that that derivative goes to 0. Basically, right? That's all it is. So from that, you can solve for the value of r, which occurs at the fixed point, which gives you the fixed point. Okay, that's not all that exciting because that's how we've almost defined the Landau theory, right? It's when r changes sign is when you go through the critical point. So it's all self-consistent, but when you have more than one parameter, you have a set of these linearized equations, differential equations. And then you have to solve those equations simultaneously to find the fixed points. Okay, that's basically how it works. Incidentally, so later on in the course, maybe near the end, I'm going to come back to this idea of L. Because for those of you that work on entanglement entropy, if you ask how entanglement entropy scales at a fixed point, you basically write the entropy in terms of this variable L, which parameterizes all the RG length scales. And you turn that, instead of looking at a differential equation, you look at an integral over all length scales. And that gives you the area law and all the subleading pieces of the entanglement entropy. So L's kind of like a useful concept. And you're like integrating over the RG length scales. Kind of strange, but it's a different type of integral. Like complication is the measure of integrations logarithmic. So we'll talk about that later. Let's just also note on H. H, which couples linearly to the order parameter. Okay, so H phi in the action. Then after an RG step, you can just basically figure out exactly how this works. This would become H. You only have one field. So Z phi prime. Have you know that scaling dimension? So you can rewrite that. So I think we can just do this. D minus D over 2 plus 1. That defines H prime, and I've set almost dimension to 0. Is there any b to the minus d's or b to the d's coming from integrals for the field? So when we were Gaussian, this phi squared term, we had a b to the minus d in that case. But it's, if there's a field, if there's field of raised to the power p, then there's p minus 1 integrals. So that's all you get in this case. So actually, it's really simple. Yeah, okay. So it is easy. So I can get YH. Okay, so I mean, you can plug it in and work through it, but that's what you're going to get. And that's right. That's the right scaling dimension. So between this and that, you can calculate all the critical exponents, alpha, beta, gamma. You know what they all are. Okay, I can't avoid the interacting term anymore. There's nothing I can say to avoid it. So let's start setting up the calculation for the interacting term. So again, we're starting with, let's go back to the 5-4 action. Any questions on this, by the way? So back to the full thing. Examples over. And I have, again, my action split into Gaussian, slow, Gaussian, fast. Okay, we've already talked about it. I erased it all. So after the integration, remember we set up an expectation value. Let's go back to that now. Over the fast fields. All right, we have that Gaussian piece out front, and then the expectation value of the interacting piece. Evaluated with respect to the Gaussian kernel, and it's integrated over the fast fields, and we dropped that constant piece that came from the partition function. Okay, so what we need is this expectation value. So it's a functional integral. There's many fields, right? We have that kernel. We have a Gaussian integral, which is your partition function, evaluated over the fast modes. So it's the expectation value of an exponential. Okay. So the first thing we're going to do to handle it is something called accumulant expansion. Okay, what that is just a mathematical relationship between the expectation value of an exponential. So I'm just using omega in place of some, for me it'll be the action. And this can be written as an exponentiated series of cumulants to different powers. It's going to be squared minus squared. That's the second power. And you have higher order ones, which we're not even going to talk about. Where does that come from? Who's seen this before? Who hasn't seen this before? Accumulant expansion. So there's a proof you can do with generating functions, but we're only going up to second order. So I think the best way to see this is just to look at both sides. So just expand so the left-hand side expand the exponential. Do it up to second order. Now the trick is knowing how these expectation values affect the sum. So you're adding up a bunch of pieces, taking expectation value, the same as taking the expectation value of every piece. So the expectation value of 1 is 1. You always expect it to be 1. This is minus the expectation value of omega, right, plus half the expectation value of omega squared, plus higher order terms. So this isn't really a formal proof, but if you look at the right-hand side, up to second order, and expand the exponential there. On the surface, it doesn't look the same. Which makes you sad, but then you go up to higher orders. So the lowest order term of the next order of the expansion of the exponential gives you, okay, so it's 1/2. And then the first term will give you this thing squared. So it's like this piece squared. And then you have higher order terms. So the only difference is somehow, you're mixing this higher order term down, and it cancels the piece that looks like what you didn't want. So this equals up to second order, left-hand side. So in order to prove it, you have to do that at every order. Okay, so just a trick, the fact that this piece, again, which comes from, it's like 1 minus this, plus 1/2 this squared. That's the first piece in this squared. It's the lowest order piece. Then you have omega-3 type pieces and omega-4 type pieces. But that piece cancels this piece, and then you get the equivalent. So that's a cumulative expansion. Okay, so we're just setting up the calculation for that expectation value. That's the first piece of the puzzle. So for us, what we want to evaluate are these expectation values. Square here. And you could go to higher orders if you want. But really, if you look up there, you just have, you're relating an action on one side to an action on the other side. So you could also write this as all squared 0. And we're only going to go to second order. So I'm just going to quit writing plus dot dot dot. So it seems simple. We have an expectation value of just the action, the interacting piece of the action, and it's a Gaussian expectation value. But we have to start remembering what that action looks like. So I haven't really been worrying about it too much, but there's 4 fields, 4 momenta. So write the delta function up front. I'm just doing a sloppy because it's in your notes. But remember, I split the field up into fast and slow modes. I did this right at the end of the class last time. So I have slow for 1 plus fast for 1. Multiplied, and there's 4 of them, remember? So then it's fast, slow for 4 plus fast for 4. So I need to do an integral, and the integral is going to have, cross terms. And will be saved by the fact that our fields, like I said last time, are only defined, within their respective shells, if you will. But we're also going to have to compute averages of, say, all these fast fields together. So we need a way to do that. Okay, and that's kind of the central problem that we have to deal with now. We have to know how to take that integral over fast modes. Right? It's the thinning of the degrees of freedom. So we're going to use Wick's theorem. Wick's theorem? Wick's theorem? You know what it is? You guys ever heard of Wick's theorem? Ever? Wick's theorem?
Heard of it.
Mm-hmm. Do you want me to derive it for you? Would you feel more comfortable, or do you want to read about it in a book? I'm not going to derive it today, so it's not going to ruin your Friday. Let me write it down first. So we need a way of taking Gaussian expectation values. Okay? Because what that means, again, is what I wrote over there. That S naught is Gaussian. Okay? So it's like a Gaussian expectation value. The partition function's a Gaussian integral straight up. There's no complication at all. So Wick's theorem tells you how to write expectation values like this out of multiple fields in terms of just the 2-point function, which hopefully, because there's 2 fields, then it looks like a Gaussian integral. Various general ways that I've written this. So the most useful, let me just imagine, maybe I have a complex variable. Let me call it something different. Psi. And I have a condition on the matrix. Positive definite means what? The eigenvalues are all positive or something and non-zero. And such that I have an expectation value of 2 fields. So the analogous thing to that, where I have some fields with this Gaussian expectation value of these 2 complex numbers, whatever they are, I'm just calling that matrix. Happens to be the inverse. So then what Wick's theorem says is, if I have a case like this, where I have many of these complex numbers, and I'll just write it in general, psi will now have to label. They have to label all the fields. So I'm going to have i's for the reals. And these will go, let me say there's n of them. Small n. And I also have complex numbers, complex fields. We're not going to use this, but let's see, 1, jn, j for the complex fields 1. Wick's theorem says that you can write that as a sum over all permutations. Of that 2-point function, if you will. So I'm calling it M, it's a matrix. I and P, I have to label my permutations. This is maybe J, let's see, N, right? M minus 1, my index I, P1, and then this will be J1. Or permutations of integers, I think it's not between, it's from 1, 2, n. So it means all the different ways that you can swap, you can permute all these integers. So this is Wick's theorem. Okay, that's generally what Wick's theorem is. But all you need is a few examples of Wick's theorem. Because you don't have n real and n complex fields. You just have like maximum maybe 4 fast fields. So let me keep it general. Talk about complex variables. So I'll call them 1, 2, 3, 4. Okay, I have an expectation value like that. A Gaussian expectation value. So it's a sum of all products of this matrix or this 2-point function. So for example, this is one permutation, 1, 3, 2, 4. But there's another one, 1, 4, and 2, 3. 1, 4, 2, 3. So it takes a 4-point function and makes it the product of two 2-point functions in 2 different ways. And that's the sum over P. Okay. So that's what we're going to do. So we're going to apply Wick's theorem to this action. So the first case will be this interacting piece. Just 4 fields, and then we're going to have higher order things here. Okay. Let's stop here because that's going to take some concentration. So the question is whether or not I derive Wick's theorem for you. I can't decide. Look it up over the weekend instead of having fun. And then talk to me Wednesday. I have a derivation, but it seems to take, I used to do it, but I don't know, it's like 3 or 4 pages of my notes. It doesn't seem like a good use of time. It confuses the physics behind the issue here, which is, let's see, 1. It's like 3 pages, so it probably will take me all this whole chalkboard, all 6 of these chalkboards. So I'll think about it. It's so completely standard that you use it all the time. If you do any sort of field theory calculations or any non-interacting systems. But on the other hand, it's worth doing once, just so you always remember. So it's like seared into your mind, like PTSD, and so you'll never forget it. So I'm not sure at which side of the spectrum I lay. I mean, this is, it's kind of opaque, but the cases where you're going to use it are sort of simpler like this. So if you just kind of believe this, you'll be able to do your calculations. Anyway, let's sleep on it. We'll come back Wednesday, and we'll continue this. But what we're basically doing is calculating these expectation values now. Okay, that'll take us a couple classes. Okay, so see you guys Wednesday.